Today we talk about how to sort of break the trigonometry that we know outside the world of acute angles. So what does trig mean when you start to talk about angles bigger than 90 degrees, right? We know that there are 360 degrees in a circle to go all the way around. So what happens if you try to take the sine of 200? Or even if you take the sine of 700 or 1000, what does the calculator do? I mean, it gives you a number, so where is it? How is it getting that? Or what's the logic that determines how a trig ratio exists and what it means when we're talking about angles bigger than 90? Because most of us, when we think of sine, cos, and tan, we think of right triangles, and right triangles always have acute angles, and everything's kind of nice. Every time you inverse, you get the answer. Every time you sine, you get the ratio. It's straightforward. But as you're going to see here, there's a lot more to this than just, using it to solve in right angles. The first thing we need to do to understand what's going on in this unit is we need to talk a little bit about what we call an angle in standard position. So basically, standard position is the idea that we can all agree that if we're talking about an angle of 45 degrees, where would I draw that on my graph? How would I graph 45 degrees? One person will probably start north and go clockwise. One person might start at north and go counterclockwise. You could start at west and go. So we need just a standard definition for how this is going to work. So I'm going to create a point O at 0, 0. I'm going to create a point A at let's say 6, 0. Okay, and then I am going to rotate point A by theta degrees. And this is what we are going to agree is an angle in standard position. I'm going to rename F to be the initial, what we call the initial arm. Sorry. Initial arm. Okay, I'm going to rename G to what we call the terminal arm. Terminal means end, right? And initial means beginning. So this is where the angle begins, and this is where the angle ends. The angle itself, which is A, O, A prime, is down here, and I don't think we need a label for it since I already called it theta, so we'll just get rid of its name. Just look at its value. And this is what you and I are going to mean when we say an angle of 30 degrees. We're gonna mean as if you started at the positive x-axis and then you rotated in a counterclockwise manner. And you can see that once you get to 360, the whole thing just starts over again. So you can, if I tell you to graph or draw a 120 degree angle, you would know what that means. You know it's 90 to get all the way up to the top, and then it would be another 30 to get to where I am. If I asked you to draw a 210 angle, I know it's 180 to get all the way over here, and then it would be another 30 to get down to 210, right? So 210 would be down like that. Okay? So this is basically what this first section is about, where it's just describing what is an angle in standard position. It starts at the positive x-axis, and it rotates counterclockwise. Again, counterclockwise just means in the opposite direction of the way a clock's hands turn, right? So that's angle theta. Okay? And angle theta in standard position is, as such. Now, when you draw an angle into another quadrant, okay, there is a second angle I want you to consider, and that angle is over here. I'm going to call this AN. Okay, this is the negative x-axis, okay, and the positive x-axis. If you take an angle in this quadrant and you measure the angle it makes with, and let's change this to a different color. Okay, this angle here is called the related acute angle, and normally it is indicated by beta. So beta equals the related acute angle. And what does it mean? It means the angle your angle makes with the x-axis. Okay, so let's just show for instance, in quadrant 1. Quadrant 1 is up here, right in the this top corner is quadrant 1. In quadrant 1, beta and theta are the same because, theta, so quadrant 1, beta equals theta in quadrant 1. Because what angle does my terminal arm make with the x-axis? Well, it makes an angle of 58 degrees, right? Whatever I measured it to, whatever I rotated it to be. On the other hand, if I go into quadrant 2, right? So, now my angle, my original angle is 128, but my beta is only 52, right? Now this is quadrant 2, so let's write down in quadrant 2, beta equals 180 degrees. Oops. 180 degrees. I don't know why it's doing that. Minus theta. Okay? So that's how you get it in quadrant 2, right? And this should make sense because a straight line going all the way across is 180 degrees. If it took me theta degrees to get to here, then it must be 180 minus theta to finish off the rest of it, right? Because my angle plus beta has to give me 180. Okay? Now in quadrant 3, and I'm just going to fix this up a bit because it doesn't quite know what I mean. In quadrant 3, okay, you can see my angle that I'm drawing is 220. Let's just make it a more round number. So let's say 240. The angle I'm drawing is 240. So I start at the initial arm. I count 90, 180, and I have 60 more to go. So that gets me down to 240. The green angle, the theta, is 240. How is the beta, the small angle, related to it? In quadrant 3, you have this relationship. Theta is equal to, or theta, let's say beta. Actually, no, it's easier to do it this way. Theta is 180 degrees plus beta. Okay? Or I guess we could, how have I been doing it? I've been isolating beta. Okay, sorry. So let me isolate beta then. So it would be beta, sorry, just do it this way. Beta is theta, take away 180 degrees. Oh my. Okay? So that's how you get beta in quadrant 3. If I ask you to draw something that's like 252, let's say, do 252 take away 180, that gives you 72, and that's what the beta is in quadrant 3. Now finally in quadrant 4, okay, beta, I'm going to hide this because it's not actually that helpful. Beta is whatever's left between your angle and the positive x-axis. So it would go kind of right here. Okay, and let me just see if I can quickly figure this out. So it would be if theta is greater than 270, I want to do the angle between A prime O and A. Otherwise, I want to do that one. I think that should work. Okay, so there's beta in quadrant 4. You can kind of think in quadrant 4, beta is whatever I would need to finish the circle and get to 360. So in quadrant 4, beta is equal to 360 degrees, take away theta. Okay, so that's how we're going to describe angles at any point in the graph. Okay, so in quadrant 1, Very easy. Beta is theta. It's pretty easy because the angle's less than 90 in the first place. In quadrant 2, beta is going to be whatever you would need to get to 180. So you do 180 minus how far you've come, and that will be whatever you need. In quadrant 3, beta is how far past 180 you went. So you take how far you went and subtract 180, and that will tell you the beta. Finally, in the final quadrant, beta is whatever you would need to get to 360. So you just do 360 minus your angle theta, and that will tell you what beta is. Okay. So if the terminal arm is in quadrant 2, 3, or 4, there exists a related acute angle beta and a principal angle theta. Okay, so we just went through that. The related acute angle is between the terminal arm and the x-axis. You're always making it with the x-axis. Did you notice I was never interested in the angle that goes angle with the y-axis, right? The angle with the y-axis, let's just say in the picture I'm drawing right now, would be right here. Let's just get rid of that B and C and the name. Okay, the angle with the y-axis we don't use in grade 11. Okay, you use it a little bit in grade 12 if you still take it in advanced functions, but you don't need to worry about the angle with the y-axis. Okay, so you're always concerned with the angle it makes with the x-axis. Okay, the principal angle is counterclockwise between the initial arm and the terminal arm. Yep. Its value can be anywhere between 0 and 360. Beta, on the contrary, can only be between 0 and 90 because beta is always an acute angle. Okay? So theta itself can be any number between 0 and 360, but beta is always between 0 and 90. So now what we're going to do is we're going to try to make sense of what is going on the calculator when I type in sine, cos, or tan of a number that can't possibly be part of a right triangle. So let's begin by looking at sine and cos and tan of 30. And if you have this page with you, you should draw this, and if you don't, just draw it on a piece of paper. But we're definitely going to want to draw these angles. So a 30-degree angle, I'm just going to approximate, is like, okay, I don't know what it thinks it's doing, but a 30-degree angle is, let's say something like this, right? It's less than 45. It's in quadrant 1, right? And that would be what a 30-degree angle looks like, something roughly like that. Now, sine of 30 from yesterday is equal to 0.5. Okay? Cos of 30 from yesterday is equal to square root 3 divided by 2. Okay? We came up with that yesterday. And again, you might not recognize this on your calculator, but what you might recognize, it might not say that on your calculator, right? So if you type cos 30 into your calculator, you're going to get this number 0.866, right? So like, again, let's just do cos 30 degrees. It gives me let's just round it to 3 decimals, 866. And again, where does it getting that from? Square root 3 divided by 2 is 0.866. So we know the exact value, but for the purposes of today, let's also just write down the approximate value so we can kind of easily recognize it from the calculator. Now, tan of 30, we know, is 1 over square root 3. Okay, and that number approximately is 1 divided by square root 3 is 0.577. Okay, so we have those values. So if you draw an angle in the first quadrant of 30 degrees, you will find that the sine is 0.5, the cos is approximately 0.866, and the tan is approximately 0.577. That's all well and good. What does it have to do with what we're talking about? Let's see what the calculator is doing when we ask it to do sine, cos, and tan of 150. And if your first thought here is, well, why is 150? Is this just a random number? How did they choose 150? Let's analyze 150. Okay, so if I draw 150, let's think about this for a sec. That would be like going a full Just this part. Okay, let's think about how to draw 150. If I drew my angle all the way down to here, that would be 180. So I need to back it up by 30 degrees. Okay, now do you kind of see why they chose the number 150? Because in this picture, okay, and let's just draw a little text box. We'll put it behind the text so it doesn't interfere. Okay, what is so important about why they chose 150 is that if you make the angle 150, then the beta, right? Remember, beta is the angle it makes with the positive x-axis. The beta is 30, right? Because from here to here is 30. And that's why this picture is related to this picture. They both have a beta of 30. This one's in quadrant 2, this one's in quadrant 1. Let's see how this makes what this does to what we understand. So I'm going to make my my theta here equals 150 degrees. Okay? And now I'm going to do sine theta, gives me 0.5 again. That's kind of interesting. That's the same answer I got in quadrant 1. If I do the cos of this number, so let's do the cos this time of theta, I get negative 0.866. So okay, I get the same answer I got in quadrant 1, but it's negative. So we don't know why it's negative yet, but we'll get there. But for now, recognizing that they're the same number is really important. For tan, right, if I go tan of theta, I get negative 0.577. So right away, our relationship brain here should be thinking, obviously there is some connection between a 150 degree angle and a 30 degree angle. Because number one, they have the same beta. The beta in both cases is 30. And number two, their sines are exactly equal. Their cosines are the same number but not the same sign, like same SIGN sign. And their tangents are the same number but they are opposites. One's positive and one's negative. Okay. For now, that's all we know. We can't figure out a pattern based on 2 pieces of data, right? But maybe based on a few more pieces of data, we can. Let's go to the next section where it says sine 210. Now again, 210 is not being pulled out of thin air. There's a reason they've chosen 210 as our number to investigate, right? And when you draw it, oh boy, hopefully you'll see why. Okay, again, I'm just going to quickly replace all these with approximately equals, so I don't have to sort of bring this with me all the time. Actually, I'll pause it and just get this done so you don't have to watch this. Alright, so when we're looking at the 210, so what angle is 210? Let's take our little blue, I guess I'll just draw another one. .210, right? Let's think, how do I draw 210? So I start at 0, and I start going counterclockwise. Here's 90. Here's 180. To get from 180 to 210, I need 30 more. So I go down there. Now, once again, right, the beta in the picture is 30 because beta is the angle I make with the positive with the x-axis, not the positive x-axis, the regular x-axis. Okay? Beta is the angle that will go right here. And once again, if you're drawing a 210 degree angle, then the beta is 30. Let's see what happens if I change my angle here to 210. Okay, notice. Sine is the same number, but negative. Cos is the same number, but negative. Tan is the same number, but back to positive. Okay, so sine was negative 0.5. I actually don't need an approximate for that. It is actually equal to negative 0.5. Cos was equal to negative 0.866. Tan was equal to positive 0.577. Okay, so one pattern that might be becoming clear to you is that when you take a trig ratio of an angle, it always gives you the same value as what it would have given you if you just took the related acute angle. What seems to be a mystery is why sometimes it's positive and sometimes it's negative. So we're going to keep going on this and we'll see if we can get to the bottom of it. For the final section, again, I'm just going to assume that what they want is beta is 30 again, but let's show how they're getting that. Okay? To draw a 330 degree angle, right? I would start at the origin. Okay? I would start over here at the positive x-axis. I'd go 90, 180, 270. I know going all the way would be 360. If I back up 30 from 360, I get to 330, right? Once again, the beta of my angle is 30 degrees. Okay? Now, let's change my answer to 330 in this picture. And my numbers are all the same. This time sine is negative, tan is negative, and cos is positive. So let's write that down. Sine is 0.5, cos is equal to approximately 0.866, and tan is equal to approximately negative 0.577. So something is definitely going on here, and we can come to the conclusion that, you know, if you give me an angle, any angle, I know that if I find its beta and check the sine, cos, or tan of its beta, it will give me the same value as your angle. It just might not be the right positive or negative. I'm not exactly sure how to get that yet. What I'm going to ask you to do today is to finish these other two. Okay? I'm not going to finish these two because you can do it yourself, and it's taking me a while to draw, as you can see, but it's not going to take you long to do this. You just sketch and, you know, plug into your calculator. It'll take you 5 minutes to do each page. I want you to finish this exercise, so finish this page with the 45 degree, finish this page with the 60 degree, and then I'm going to open up a discussion on the website where I want you to note patterns that you see. Okay? What patterns do you notice? And then at the beginning of tomorrow's lesson, I don't think we're going to do a lesson tomorrow. We'll do it at the beginning of next week. I will make sure, of course, that we get the right answers, but I really want you to think about this and explore this on your own. So come up with an idea, a theory, a pattern, anything you notice, even stuff I've already talked about, just put it in your own words. It helps to do that, okay? I'm going to leave these ones. I am going to go down to just talk about this bottom part for a sec. It says, an angle in standard position is determined by a counterclockwise rotation, and that is always positive. But what if you were to rotate in a clockwise direction? So let's just go back to my original thing here and say I'm allowed to rotate in a negative direction as well. If you rotate in a negative direction, right, it's just like rotating clockwise. Right? So you see I'm turning the way a clock is turning now? So if I rotate in a negative direction, it goes clockwise, that's all. Okay, so, excuse me, an angle determined by a clockwise rotation is negative. So, you know, if I asked you to draw, for example, let's draw the angle negative 60 degrees. Okay, so the angle negative 60 degrees would look like this. Okay, so you would start at the origin, and you would I can't get this to line up. Normally you would rotate 60 degrees going up, right? But if you're going negative, you just go down. So there you go. There's a negative 60 degree angle. So let me just just want to grab a text box from up here. I can copy paste. Oops. GeoGebra shortcut doesn't work in Word. Okay. Here, what I've drawn is negative 60. Okay, this would be an example of drawing negative 60. Now, my question for you that I'm going to post right now, another question I want you to think about. I'm going to say, draw these two angles in standard position. Describe their relationship. Okay? Number one. Let's just see if I can get the theta here. Theta, oh boy. Okay. Theta equals negative 60, and theta equals 300. Okay, I want you to draw those two and see if you can come up with anything that's how they might be related. All right. Now, which negative angles in the Cartesian planes have primary trig ratios that relate to the 30-degree angle? Well, they would need to have a beta, right? Oops. They would need to have a beta. Oops. Beta equals 30 degrees. So the answers would be negative 30, right? Let's just draw them quickly. So there's a negative 30. Then you would draw a negative 150. Right? I'll write down the numbers underneath them. So this is negative 30. This is negative 150. The next one is, so again, I start from 0, negative 90, negative 180, 30 more is negative 210. And finally, let's do the same thing one more time. Started at 0, negative 90, negative 180, negative 270, negative 360, but then I have to back up 30, so I get to negative 330. Okay. So that would be how you would draw a bunch of related angles, but negative. And again, if you want to post on my discussion forum, how are these numbers and their sines, coses, and tans related to what we just did at the top with the 30 degrees? Okay. When you're done this, you should be able to fill out this chart. Okay, again, I will start our next lesson with filling out this chart, but I want to challenge you to do it because I want you to look for the patterns in what we just did. Okay, because if you can see the patterns yourself, you stand a much better chance of learning it. Okay, so go back, finish the blank sections here, the 45 and the 60, and then look for patterns and post about them. And again, feel free to post about patterns I talked about. That's fine. It doesn't have to be something new. Just get on there and write down what you see and what you understand, right? And that will help make it more clear in your mind.